We're back with the second half of the wave characteristics notes. We're going to start with period. Period is very, very, very simple. There it is. Forgot, I almost didn't find my period demonstrator. Okay, period is very, very, very simple. Period is simply the time required for something to happen one time. When we're talking about waves, one complete vibration of the wave to occur, but it really could be anything cyclical, anything that goes in cycles. So for example, I've got a ball swinging on a string, okay? Every time it goes around once, so let's say it starts right when it gets to the top, okay? Every time it gets back to the top, that is one period. If I do it at a constant rate, we could measure the period. So period would be from now, okay? It's very, very quick. If I have a bigger string, I suppose it takes a little bit longer. So between there and there, that's one period. If I make the period smaller, okay, that's a much smaller period, okay? It's a lot less time for something to happen. On the reference tables, page 5, period is symbolized as capital T, which makes sense. Lowercase t, as you know, is time. Period is a time. It's just very specific time. It's a time for something to happen once, and therefore it is symbolized with a capital T, and it's measured in seconds. The reason I'm going on so much about period is because people will get it mixed up with this next one, which is called the frequency. By the way, if you want, you can go back to the front of this, and you know how we left some space on this arrow right here? We said this was the wavelength. Well, it turns out this could also represent the period if you have, let's say, time on this axis. If this axis is time, then this would measure, okay, so let's say it's like 0 seconds, 1 second, that would be the period. If, on the other hand, this axis measures distance, okay, so like 0 to 2.5 meters, that would be wavelength. So you need to be able to read the axis, as I've been telling you all year. You have to actually read the graph. You can't just look and assume you know what it means. So let's scroll back down. Okay, there we go. So, anyways, yes, what I was saying was period and this next one, frequency, get mixed up all the time. Period is how much time it takes for something to happen once. Frequency is how many cycles or vibrations or events happen per unit of time. Almost always per second, but I'm going to give you some examples right now that are not per second. Some that you know of and use every day, okay, or maybe you use every day, but you have definitely learned about your heart rate. Your heart rate is measured in beats per minute, right? Beats per minute. That is a frequency. It's how many times your heart goes through the cycle of a beat per 60 seconds or per minute. RPM, anyone who knows a lot about cars or motors knows that how many times a motor turns over per second is measured in revolutions or rotations, someone's told me, but I'm pretty sure it's usually revolutions per minute. Essentially how many times a motor turns over per minute, usually in the thousands. Okay? Frequency is commonly measured not in seconds, it uses seconds. Like I said, it's usually, we base this on seconds. And the unit itself is typically referred to as 1 hertz. Abbreviation HZ, which is equal to a 1 over seconds. And this is symbolized, the symbol for frequency. Of course, I've written straight over it. It's right here, it's right under speed of light in a vacuum. It is a lowercase f, okay, the symbol for frequency. Uppercase F is for force. Lowercase f is for frequency. Now, let me go back to my ball and a string example, okay? So period is the amount of time it takes the ball to go from, let's say, the highest point to go all the way down and through and get back to the highest point. The frequency, on the other hand, is how many times that event, the ball going through one cycle, happens per second, okay? So right now, this is probably a period of about 1 second. That also means the frequency is about 1 second, okay? It's happening about once per second. On the other hand, if I shorten the period a lot and I do this and I spin so that the period is very, very short, okay? Very short amount of time, turns out that the frequency increases. The ball is making more than one cycle or going around more than once every second. So the frequency is simply counting how many times the ball goes around per second, okay? They're very, very easy to get mixed up, guys. You have to make this, you have to really think about this one. especially when you're just starting off. They're very closely related. They apply not only to waves, as I was just showing you, but any motion that is periodic. Some examples. Let's say there are 2 cycles. I'm going to use wave examples here. Let's say there's 2 cycles of a wave happening per second. Okay? 2 cycles per second. That is the frequency. The frequency right there is 2 hertz, Hz. Okay, that's this unit for it. What is the period of the wave? So 2 waves happen per second. Well, if 2 are happening per second, how long is each period? Or how long is a period? How long does just one wave take? If you think about it for a little while, you'll come up with the answer that the period must be half a second. Okay? After 1/2 second, you've done 1 wave. After 1 full second, 2 waves have happened. Another example. A wave has a period of 0.2 seconds. How many waves happen per second? In other words, what is the frequency? Okay, what is the frequency? Well, this one you can think about too. Okay, nice easy numbers. 1 wave takes 0.2 seconds to happen. So 2 waves is 0.4 seconds. 3 waves is 0.6 seconds. 4 waves is 0.8 seconds. And 5 waves would happen in 1 second. 5 total waves. So that means the frequency must be 5 hertz. And if you look at these numbers, there's something special about these 2 numbers. Okay, 2 and 0.5. They do something kind of strange. And there's something special about these numbers, 0.2 and 5. And usually in class I would let you kind of figure it out for yourselves, but here I'll just tell you, what do you get if you multiply these 2? You get 1. What do you get if you multiply these 2? You also get 1. So what this tells me is if I take the frequency and I multiply by the period, I will always get 1. Now, of course, it's not written like that in the reference tables because that looks really silly. The way it's written in the reference tables is something like this. Let's get t by itself. We divide both sides by f. Comes out to t equals 1 over f. Okay? Or the inverse of that, or the reciprocal of that, what if I divide both sides by t? I would have f equals 1 over t. So from this, you should be able to see that frequency or period are inverses of each other. They are inverses. And I'll get to this example in just 1 second. The equation that describes their relationship is this. T equals 1 over f, or you can also use f equals 1 over t. That's what inverse means. So, in this case, it says a bike wheel undergoes 1 complete rotation every 0.12 seconds. That is the period. That is the amount of time it takes for one cycle to happen. So that's t. We want f. So we simply take 1, divide by 0.12 seconds, and we come out with a frequency of, I believe, you can check this for yourself, 8.333 repeating hertz. Okay, that is the frequency of that. And again, notice, every frequency and period are not the same thing. They're inverses of one another. So they look very, very similar, but they are not quite exactly the same thing. And again, as I'm erasing this, as soon as I'm done, I'll show you where this equation is in the reference tables. It is the second equation down. We'll do the first one in just a second. It's the second equation down on page 5 under waves right here. T equals 1 over f. T being period, f being frequency. Okay, we'll do this one in just a second because that's our next topic, speed. But we got to finish this up. Okay, the frequency of a sound wave. Okay, what is the frequency of a sound wave tells us? That tells us the note or the pitch or the tone. Okay, those are all basically words that mean the same thing. Note, pitch, tone. Tells us how high or low the sound is. Okay, that's our general description of it. Frequency of a light wave is much more interesting. The frequency of a light wave actually tells us the color of light that we are seeing. We're going to spend a whole day talking about light. Okay, actually spend more than a whole day talking about light. We'll talk about light for a couple days. All right, light is very interesting. But you should know frequency of a sound wave means the pitch or the note. Frequency of a light wave means the color. Let's get down to our last topic in wave characteristics, just kind of like general information to know about waves. That is how fast they travel. Waves travel over distances. You guys have seen this, okay? If I take a slinky and I shake it, the wave moves through space. We can measure how fast they move, okay? These waves move at different speeds depending on the medium they're moving through. Wave moving through a loose slinky moves a lot slower, I believe, than a wave moving through a really stretched out tight slinky. The formula for calculating a wave speed is this: V equals F lambda. And that is the first equation in the wave section on our reference tables. V equals F lambda, lambda being wavelength, remember. So the velocity equals the frequency times the wavelength. And if that seems like a really weird equation, just know that I probably spent at least 2 hours thinking about this one time. I was in Regents Physics, it was towards the end of the year, and I learned V equals F lambda. And I was like, why would you take the frequency and the wavelength and multiply them? How is that the speed? And it literally kept me up at night one time. Like, I'm not exactly proud to admit. But it does kind of make sense. Let's say that you are standing at a spot in the water. This is a super non-realistic example, but it kind of illustrates my point. Let's say that you're standing in the water at the ocean, and there are 5 waves that are all 5 meters long, 5 meters between crests, okay? So you've got a crest here, then 5 meters away, so this room is about 10 meters wide, so you're standing here, 5 meters away is the crest of another wave, 5 meters past that is the crest of another wave, and so on and so forth. Okay, the waves are 5 meters in wavelength. And let's say that 4 of those waves pass you in 1 second. So the frequency is 4. So, if you think about it, 4 waves pass you and every wave is 5 meters long. They're all just kind of moving in a row. Well, the first one passes you in 0.25 seconds, okay? And then, if it starts right with you, that means after 0.25 seconds, it's now 5 meters away. And the next wave is at you. And then 0.25 seconds after that, now the first wave is 10 meters away. And then after 0.75 seconds, it's 15 meters away. And then after 1 full second, as that 4th wave reaches you, the first wave is now 20 meters away. Okay? So that wave has moved 20 meters in 1 second. Now, if it's moved 20 meters in 1 second, 20 meters per second, hey, guess what? That's a speed. Okay? This equation does not replace your other equation for speed, V equals d over t. It is just another way of finding the speed, especially if you don't know how far the wave has traveled and how much time it's taken. If you simply know the frequency and the wavelength, you can figure that stuff out for yourself. So this equation does make sense. I urge you to think about it for a little bit. Okay? Here's one that always gets me. People do not know this, and it shocks me. I don't know why. I don't know if you just didn't pay attention to this in elementary school, or if it's just something that's not taught, but I can't imagine that. I don't know. I mean, I grew up with Bill Nye and Miss Frizzle, and I loved all those shows. Maybe I was just a nerd and paid attention, but I just thought this was common sense. When we have a thunderstorm, there was a really bad one last night. Lightning always comes before thunder, guys. It's not the other way around. People were trying to tell me that they hear thunder and then see lightning. It's different thunder and different lightning. All thunder is preceded by lightning. I'm not going to get into the mechanics of how lightning creates thunder, but it does, okay? You see the flash first, then you hear the thunder. If you hear the thunder first and you're like, that came first, you just missed the lightning, okay? You weren't watching or something, all right? Anyways, the reason we see lightning before we hear thunder is because light waves travel much, much, much faster than sound waves. And we're going to head back to the reference tables right now. We're going to go to the front of the reference tables, actually, okay, to the constants section. And it's right at the top. Speed of light in a vacuum. Vacuum means empty space, but it's pretty much the same thing in air. The symbol is c, lowercase c. Look at this, 3 times 10 to the 8th. That is 300 million meters per second. Speed of sound in air at STP, chemistry reference, standard temperature and pressure. Not too important in physics, though. 3.31 times 10 to the second. 10 to the second is 100, so 100 times 3.31 is 331 meters per second. One of these is a lot bigger than the other. The speed of light is much, much bigger than the speed of sound can be. Okay? So the speed of light in a vacuum is c. It is 3 times 10 to the 8th meters per second. And the speed of sound in air, 3.31 times 10 squared meters per second. We're going to write a couple of extra things next to that. These can change. There's a reason it says in a vacuum and in air at STP. Speed of light is different in every medium. Any different material, light will travel at a different speed. Okay, we won't get into why just yet, but the speed is typically lower in denser materials. You can think of it, I guess I will get into it. You can think of it as light has to, if there's more materials, there's more things in the way of the light, and the light has to kind of bounce around off all those things. And it ends up going, in general, slower. Speed of sound is also different in different materials. So different in every medium, but it's the reverse of light. Speed of sound is actually higher in denser materials, and that has to do with how sound works. Remember, it's a longitudinal wave. Sound works because you have all these particles that are bouncing off each other, and the pressure wave, that's what sound is, moves outward. If there's more material there to bounce around off of, that wave will propagate through the material quicker. Okay? So, speed of light in a vacuum, speed of sound in air. Light is much faster. These can change in different media. Light moves slower in denser materials, sound moves faster in denser materials. 3 examples to close out. Let's say we have a sound wave has a frequency, sound wave in air has a frequency of 440 hertz. I believe that's like concert A or C or something like that. What's the wavelength of this note? We just figured out the equation, V equals F lambda. We are looking for the wavelength, we're given the frequency, and you might be like, well, how fast is it moving? It's a sound wave in air. We got to assume STP. So, 3.31, you can write 331 if you know that that's the number. Just make sure that you don't write like 3,310. Frequency is 440 hertz. There's lambda. If you solve this, okay, divide this by this, you should end up with a wavelength of 0.752 meters. Wavelengths are measured in meters. Okay? All that means is that the distance between successive compressions or successive elongations is about 3/4 of a meter. About that much. Okay? That's the wavelength of a sound wave. Now let's talk about light. A type of green light has a wavelength of 5.89 times 10 to the negative 7th meters. What is the light wave's frequency? V equals F lambda. Now we're looking for frequency. For speed, we're going to use this. 3 times 10 to the 8th meters per second equals F times 5.89 times 10 to the negative 7th meters. By the way, 10 to the negative 7th meters, you can't even imagine how small that is, okay? This is tiny, tiny, tiny wavelength. Please make sure you know how to use exponents. It's that time, you have to know, okay? If you don't know by now, like, I don't know what you've been doing all year. You really have to know how to use your calculator, okay? It's crucial. You divide these two, you get a frequency of 5.09 times 10 to the 14th hertz. And if you seriously don't know how to use your calculator, please just ask. I'll show you how to do it. You got to pay attention. What does this mean? This means that light goes through its cycle 5.09 times 10 to the 14th times per second. That is, let's see, billion, trillion, 50 trillion times per second the light wave is going through its cycle. Like I said, you can't even imagine that number, okay? The reason that's so big is because look at the size of these numbers. This is really big, that's really small. Last question for these notes. Let's say lightning, this is a practical application. Lightning strikes 3 kilometers away. Find the times for the light and sound waves to reach you. We'll do light over here, and we'll do sound over here. Now, you are not given, for this one, the wavelength of the frequency. So you're like, well, how do I figure that out? You are given a distance, and you do know how fast each of these types of waves travels, and we're looking for time. We're going to actually fall back to our good old V equals D over T. Just because it's a waves unit doesn't mean we can't use this. It's just that this is going to pop up more and more. But I want you to understand that we can use this as well. For the light wave, or the light from the lightning reaching you, that light moves at 3 times 10 to the 8th meters per second, 3 kilometers. Hopefully we can unit convert by this point. That's 3,000 meters. The time that it takes that light from the lightning 3 kilometers away from you, I'm at school right now, 3 kilometers away is like Riley's, okay? So if lightning strikes Riley's, and I'm looking out the window towards Riley's, that light would take 1 times 10 to the negative 5th seconds to reach me. Or if you don't like scientific notation, 0.00001 seconds. That is much too fast for you to even register that it's happening, okay? If you try and stop a stopwatch, if you do start, stop, the shortest amount of time you guys are going to get is like 0.07 seconds, okay? That's like 7,000 times faster than this, or longer period of time than this. This is almost, it looks instantaneous to us. It's not, but it looks instantaneous. The thunder, on the other hand, maybe some of you guys have heard that old trick where you see lightning and then you count how many seconds until you hear the thunder, and then you take the number and multiply by 5 or something. That's how many, or divide by 5. That's how many miles away or kilometers away something is. Anyways, the speed of sound in air is approximately 331 meters per second. We get that from here. I just use the normal notation, not scientific. We divide that, or no, we don't divide that. We plug in our 3,000 meters. There's our time. Well, light, which reached us from lightning in 0.00001 seconds, is so much faster than the sound reaching us. That sound takes a little bit over 9 seconds to reach us, if you do the math there, okay? Please, lightning reaches you before thunder does. If you hear thunder and you're like, I didn't see any lightning, well, you just didn't see it, okay? Maybe you were looking away, maybe you just missed it, or you had your eyes closed or something. Literally, if you blink, you could miss it, all right? That is wave characteristics. There's two more pages that we would do in class, but I guess I would say that they're kind of combined. They're not really separate topics. It's kind of a combined section on wave phenomena and interference, and I will be back to do those at some other point. So, have a nice night.